Welcome to our Spring 2022 Ionic Viper nanoCHAT YouTube video series. NanoChats are short videos where members of the community come together to engage critically reflective teaching practice and share our experience with our peers. I'm Lori Watson. I'm an inorganic professor at Earlham College in Richmond, Indiana. This semester, the theme of our weekly series is nanoCHAT NeWBiEs. We'll be capturing what it's like to teach inorganic chemistry for the very first time in real time, week by week. I think we're on week 4. We'll be hearing from 2 Ionic members this semester who both are teaching at the U.S. Naval Academy Chemistry Department, Wes and Shirley Lynn. How did it go this week?
So this week we did the second part, the last part of chapter 2, which was simple MO theory, diatomics, and then we started symmetry. And one of the big things that I learned about MO theory is that, and I know it's shocking, if you look stuff up on the internet, sometimes you find wrong things, including wrong MO diagrams. So there was like a moment this week where I just reached out to Ionic members and I was like, what's going on with carbon monoxide? I don't understand all these different diagrams. They're simplified diagrams, which apparently are just wrong. And then there are diagrams that are labeled different ways. So, sometimes people label them with a star to indicate, anti-bonding, or they don't label them anti-bonding or non-bonding or bonding at all. They just say sigma and pi. And so it's a lot to navigate. And I think one of the good takeaways from this week for me and hopefully my students is that there's this tension, right, between Lewis structures and MO theory, where Lewis structures, we like how simple they are, but then they don't give us the accurate picture. And then MO diagrams, they give us a more accurate picture, but then also the orbitals are hard to interpret. And so the messiness of all those models, I think, opened the door to really, really good thoughts and conversations. And I'm looking forward to next week when we do more than 2 atoms for MO theory.
Mm-hmm.
Yeah, I did the same thing, and I noticed the same things. One thing I did is I went through with them, we did the molecular orbital diagram for oxygen, and then once we had it, I asked them, what's different about this than what you would expect from Lewis theory or valence bond theory. I thought they would notice at first. They didn't figure it out right away. So what it is, I just quickly pulled up a video on YouTube of somebody pouring liquid oxygen between 2 magnets. And they quickly saw that it's magnetic, and then we're able to make that relation back to the molecular orbital energy diagram. So it was a good way to show how molecular orbital theory is really giving a much clearer, much more full depiction of what is happening in the electronic structure of these even very simple molecules, and really just where the more simple theories like valence bond theory and Lewis theory falls apart. We used it to predict things. So I asked them to predict whether the ionization energy of the NO- anion would be higher or lower than just free nitrogen or free oxygen. And they were able to see that it should be higher because all the electrons, or at least the electrons in the HOMO are in a bonding orbital, and that's a stabilizing interaction. And we also saw how when you look at something like nitrogen monoxide, I asked them to find where is that radical located. Is more on the oxygen or more on the nitrogen? And then once they said it was probably more on the nitrogen, given that it's in an anti-binding orbital with more nitrogen character, they were able to then look at a Spartan molecular orbital diagram and see that it is in fact much more localized on that nitrogen. And that led to a bit of a discussion about bonding of the NO molecule with transition metals and how that manifests itself in real life. So it really has been a fun experience, even if it's a bit challenging, that we're able to show them this much more powerful theory that is better able to describe what we really see in the world. But on that note, Lori, I know you do some computational chemistry. I was wondering if you had any thoughts on that, doing these MO calculations using Spartan or other programs.
Yeah, that's a great question, and I'm glad you incorporated into your discussion of MO. I think computations is a way to at least make the messiness a little more visual to students. So in my class, our first lab actually is a lab using the WebMO interface to Gaussian. And we do a lab on VSEPR theory and looking at, bond angles and geometries and how different periodic trends affect that. And so my students have already learned how to use some basic computational tools. And so in this section of MO theory, I have them running real-time calculations in class of some diatomics and making some predictions by groups. I have different groups doing different things, exactly like what you did with Spartan. Like, where would the HOMO be, right? Where's the charge, extra electron? Why is CO so much different, or oxygen, even O2, so much different than why you might or how you might do it in a Lewis structure way? It looks a lot more complicated, right? And there's a lot more mixing of orbitals that we certainly don't talk about in general chemistry. And we do some MBO calculations, which is another way to sort of visualize orbitals. So it really gives them an idea of exactly what you both said, that MO theory is messier, but gets you closer to the right answer as determined by experiment. So it's a lot of fun. And it's fun to incorporate symmetry into that too. And I heard you guys started Symmetry this week.
Yes, and I just want to give a shout out to the Otterbein Symmetry site, which I know is a Viper LO staple. So both Wes and I used it, and I'm also using Kyle Grice's LO that employs the site. And I just want to mention to the people who are watching the YouTube video that we will link these resources to the notes for the video, so you can find them. And those include not just the LOs, but also a slither that Dean Johnston at Otterbein, who is the creator of the site, did for us. I think it was like a year ago. It's a great slither, and I just encourage people to look at it and learn from it. So if you've not taught symmetry with the site before, highly recommend it.
Yeah, it's been a great tool. I brought in models and had them looking at the models when we're talking about symmetry. But that Otterbein site does a really good job of visualizing it in a way that even a model can't. So the students are really enjoying it. One of my students said that she finds it oddly satisfying, and she's planning on using it as a way to like kind of calm herself down before she goes to sleep. So I don't know if she's actually done that or she was just saying that, but I don't know. I enjoyed that. They enjoyed that so much.
I love symmetry too. The Otterbein site is perfect. I use it when I teach, and I often have them go and do a scavenger hunt on campus for symmetry elements. I think there's actually a few versions of that on Viper too. And so I was thinking of that just as you were saying, your student finds it oddly satisfying. Just tell her that symmetry is everywhere and she can find the point group of anything, and her life will never be the same.
I wanted to jump in and ask something that's not sort of related to content. It's week 4. I've gotten to know my students, I think, pretty well. It's we're still masked and everything in the classroom, but I know their names. And I'm noticing this sort of disparity in amount of participation. Like, I have 6 women in my section, and I was just thinking about it. They tend to be quieter. They tend to not be the ones that are engaging when I'm asking questions, or and I just would love to kind of get some thoughts on how to improve that engagement. And I have to say, like, when I was a student, I was not somebody who was immediately there raising the hand, right? I was more on the quiet, introverted side, and so I get that. But at the same time, I think they have valuable things to say, and I want them to feel like they can participate.
Mm-hmm. Mm-hmm. Wes, are you seeing the same kinds of things?
Yeah, I'm seeing a bit of uneven engagement as well. The way that I am trying to get around that, because when I ask questions to the class, I don't do the thing where I kind of like do like a random selection, just because I didn't like that when it was done to me. So I have a hard time doing it. Maybe I should, so I'm considering it. But it is the same people who tend to respond to my questions. But unlike Shirley, I have a long period each week. So rather than meeting 4 times for 50 minutes, I have one period that I meet that's twice as long. So normally what I've been doing is during that time, half the class, I give them a worksheet and I tell them to work in small groups. And then the people who don't seem to chime in front of the entire class, they are participating in their smaller groups. And then I come over and talk to them, and then they talk more one-on-one to me, or like, 3-on-1. So I'm finding that that's a way to get these people who don't want to speak up to the entire class to be somewhat more involved and not just be passively taking in the information. That's a bit of a luxury that I have, but I think it's a little bit more difficult when you don't have these long periods. The names are an issue though. They are all masked and are wearing uniform, and it's cold outside, so they're wearing jackets, so I can't see their name tags. So I know like 3 names out of 16.
Yeah, names are always a challenge, and with current COVID restrictions, even more so. I think small group is a really great engagement strategy, and you can do some of that even in shorter classes. Another thing that's similar is doing kind of a think, pair, share activity. Sometimes students are reluctant to speak up because they're not sure they know the answer, or they want someone else to confirm that they're along the right track thinking. And so talking first with a neighbor has them practice saying the answer to whatever question you're asking, and then it's not too bad. Sometimes they'll volunteer, or even if you do call on them kind of randomly, you can kind of get a sense based on your observations of them talking in pairs, like, oh, this student who doesn't often speak up is actually talking to their neighbor, so they might have something to share with the class. And so that's another strategy that's similar, I think, to the kind of breakout groups, small group participation. Well, it sounds like you guys are having a great class. I think next week you're headed on to doing even more symmetry, and then using that in MO diagrams of larger molecules. That's always really fun for students, and so I'll be excited to see how that went next week. So thank you for this great conversation, and to all of you who watched the video, please feel free to comment about this nanoCHAT NeWBiEs episode in our Ionic Discord, and check out the links to the resources that were mentioned in the video. Join us next week.
Thank you.
Thanks, Laurie.
Thanks.